Next, I'll look at the initial responses of the cardiovascular system. The CV system is made up of the heart, blood vessels, and blood. It is responsible to transport oxygen and nutrients to the body's cells, as well as remove waste products made during internal respiration, such as carbon dioxide. During a warm-up, the body will produce more carbon dioxide than at rest, which means it needs to be removed and oxygen needs to be brought back into the body quicker. Heart rate is the number of times the heart beats per minute, as the heart will have to pump blood more frequently. This means that heart rate will increase during a warm-up. Stroke volume is the amount of blood that is ejected out of the left ventricle with each contraction of the heart, measured in millilitres. As the body requires oxygen at a higher quantity, the heart's contractions will be stronger to pump more blood, therefore increasing stroke volume. Heart rate multiplied by stroke volume is used to calculate cardiac output, which is the volume of blood pumped out of the left ventricle per minute, measured in litres per minute. As the heart beats more frequently and contracts stronger, the cardiac output will also increase. However, as heart rate is increasing, it only gives the heart so much time for the atria to fill with blood during the cardiac diastole phase, which is when it is relaxed. This means that there is a point at which stroke volume will plateau, as only so much blood can get into the heart before it contracts. From this, for the cardiac output to increase further, it relies on heart rate to keep rising. Heart rate is controlled by the autonomic nervous system, which means that it is out of our control. The cardiovascular system features receptors in different forms. There are chemoreceptors that detect changes in the chemical state of blood, thermoreceptors that watch the body's temperature, and baroreceptors that measure tension in blood vessels. During exercise, the body will start to produce more carbon dioxide than at rest. This means that a higher volume of carbon dioxide is in the blood, decreasing its pH, making it more acidic due to the hydrogen ions. Chemoreceptors will feed this back to the cardiac control centre in the medulla. In response, the SA node, which is the heart's pacemaker, needs to receive an impulse to increase the heart rate. The cardiac acceleratory centre will send an impulse down the accelerator nerve, which is a sympathetic pathway to the SA node. The axon terminals will secrete norepinephrine, which is a neurotransmitter that initiates an increase of the rate and force of the heart's contractions. The graph shows how an athlete's heart rate changes throughout the multi-stage fitness test, from resting at 78 BPM to 176 BPM at stage 8. This shows how, as intensity increases, the body needs to work harder to supply muscles with oxygenated blood, therefore the heart will beat more. As this increases, it will cause a knock-on effect of an increase in cardiac output, as more blood leaves the heart per minute. After the activity is concluded, it is shown by the graph that heart rate has a rapid decrease back down towards resting level. A winger in football is likely to see a rapid increase in cardiac output. Their role on the team will mean that they need to attack by beating players, as well as helping out defending. This means that their heart rate will naturally see a high increase due to the intensity, with little breaks to recover, as heart rate and intensity have a linear relationship. As well as this, stroke volume will increase to supply their muscles with oxygen and remove carbon dioxide quicker, so that they can resist fatigue for as long as possible. A consequence of these values increasing will mean that cardiac output will rise as the heart beats more per minute and more blood is leaving the heart with each contraction. The cardiac output graph shows a rapid increase at the beginning of the test, gradually become a more steady increase. This will be because the body demands an abnormal amount of oxygen at the start of the test. Then, as the heart rate increases, stroke volume will begin to plateau as it reaches the maximum. Therefore, the heart rate will need to continue to rise to increase cardiac output, which is apparent. Similarly, to the heart rate graph, cardiac output took a rapid decrease after the test, as the body's demand for oxygen will be decreased. Therefore, chemoreceptors will recognise a higher volume of oxygen in deoxygenated blood. This will mean that the autonomic nervous system will choose the parasympathetic nerve pathway to decrease heart rate and stroke volume. Blood pressure is the force that blood applies against blood vessel walls measured in millimeters of mercury. It is written as a number on top of a smaller number. The large number on top is a systolic blood pressure, which is the pressure produced in the arteries during a heart contraction phase. A resting value for this is 120 millimeters of mercury. The bottom number is the diastolic pressure, which is the blood pressure between contractions. The average resting value for this is 80 millimeters of mercury. The change in blood pressure can be calculated by multiplying cardiac output by the resistance to flow produced by the arteries. The resistance to flow can be affected by different factors like the viscosity of blood, vessel length, and vessel diameter. The viscosity of blood is how thick it is. When your body is colder, your blood is likely to be thicker, which will increase your blood pressure. Likewise, dehydration can lead to a higher viscosity of blood. A blood vessel's length is directly proportional to the resistance. Therefore, the longer the vessel, the higher the resistance. The diameter of arteries can affect resistance, as the thinner the artery, the higher the resistance, and vice versa. Hypertension will mean that the heart needs to work harder to supply the body with blood. This can also contribute to the toughening of arteries, called arteriosclerosis, which can lead to stroke and heart failure. However, blood pressure homeostasis can be achieved by the autonomic nervous system altering the diameter of the arteries and arterioles. Baroreceptors are found in the left and right carotid artery, specifically the carotid sinus, which is the bulge of the vessel before it splits, and also the aortic arch. These detect the stretch of the vessels by recognising the change in tension of the vessel wall. This information will be fed back to the medulla, where an impulse will be sent down one of two pathways, sympathetic or parasympathetic. The sympathetic pathway will trigger vasoconstriction of the blood vessels, which is the narrowing of the vessels. This will increase heart rate and stroke volume to increase blood pressure. On the other hand, the parasympathetic pathway will cause vasodilation. This is the widening of the diameter of the blood vessel. This will lead to a drop in heart rate and stroke volume to decrease blood pressure. The two graphs show the difference between the impact of submaximal from early stages of the multi-stage fitness test and maximal intensity from the Wingate test on blood pressure. During submaximal exercise, systolic blood pressure should see a linear increase, whilst diastolic blood pressure has a slight change. The systolic value should see a plateau at around 140 to 160 millimeters of mercury. On the other hand, the Wingate test results shows how during maximal exercise, systolic blood pressure will have a linear increase and diastolic should not really change. The multi-stage fitness test results can resemble the expected values for a central defender during times when they are not really involved in the game, but may see small increase in intensity. Whereas the Wingate test may resemble a short counter-attack, as they need to work maximally to defend until the danger is over, which is usually no longer than the Wingate test, which is 20 seconds.